So who's got this first one? It's probably pick a man. Break it down for me. What'd you write first?
74 out of 100.
Yeah, 74 men. So how many chances do you have to pick a man? 74 out of how many total things could happen? 132. That's the basics of probability, right? What's probably a roll of 1 on a 6-sided die? What's probably a roll of 1? 1 out of 6. Because there's one side that matches what I want out of 6 sides total, assuming it hasn't been tampered with. All right, be careful who you play with. All right, don't be playing it. All right, stop with that PSA. So probably a man. There's 74 total men out of 132 total people. That is the percentage of men, but it's also the probability that I pick a man. So percentages and probabilities are very closely related. They're sometimes the exact same thing. And what'd you say? I'm sorry? What was that roughly? 56?
Yes. 56%.
Thank you.
I'm good.
I got water. Okay. All right, so what's probably pick somebody who said no?
47.
Yeah, 62 out of 132. So what was it? 47. And then what about the probability that I pick a woman who said maybe?
5 out of 11.
Say again?
5 out of 11.
Good. There's 5 women who said maybe. So the top, it looks like probabilities work this way. It looks like the top of a probability is the number of things that match what I'm looking for. And the bottom is all the things that could happen. That's how basic probabilities work. I'm getting a look like, well, duh, yeah, but not everybody knows this. Not as many as used to know it, actually. I don't know what they're teaching anymore in high school at all. Not that. So probably a woman said maybe, 5 women said maybe out of 132 total people. 4% roughly?
Yeah.
Roughly 4%. Okay. You left something in here? Ah! Okay. All right. So let me ask you another question from this. Notice how the bottoms are always 132. Why is that? For all the questions I've asked you so far, do you know anything about the person that was picked? To start with, I don't know shit. These are all questions. Okay, pick a person. Okay, what's probably that the person was a man? It could be anybody. What's probably the person said no? It could be anybody. What's probably that it was a woman who said maybe? Still could be anybody. Could be a man that I picked. What's the probability that it was this type of person? That's very small because there are very few people that match that description. So this is a very different question I'm about to ask you. What's the probability that I pick somebody who said no, given that it was a man? Give me the fraction. The fraction is what I must see. And then you can make a percentage if you want to after that. The fraction is your work. I like it.
Wait, no.
You ready? What do I know about this person? I know something now. What do I know about this person? They're a man. How many people could it be then?
74.
So what's going to be at the bottom? 74. So it's always out of the total it could be. So I throw all these people away, or maybe I just tell them to move to the other room. I don't throw the women away. I say move to the other room. Now I've only got 74 people that I'm talking about. Out of those 74 people, how many match what I'm looking for? 51. Yeah, whatever it is. What was it, sorry? 69%? So, all right, let me stop there for a second. We're kind of doing an overview, and then we're going to get deeper into a lot of these ideas, but I want to show you how the calculations are pretty straightforward. Some of the theorems and some of the freakier stuff we'll get into later, but right now I want to show you the semi-easy stuff. When it's given to you in a chart, it's so beautifully easy. Whatever you're given this, then you cover everything else up and you live in that. So if I would have said, given that they said yes, I would have done this, and that would have been everybody for me. You guys see that? Only live in that one thing you were given, because that's all it could be. Would you say that gender affects the answer given? You would have probably said that beforehand, but now I have definitive evidence. What was probably that a person said no, period? What was probably a person says no? 47%. How did it change given that it's a man? It went up. Yay, all right. It increased, right? The probability that they said no increased given that it's a man. So we see this kind of thing all the time. Whenever you see something broken down by demographics, those aged 18 to 34 actually said, blah, blah, blah. All right, that's this kind of, given that they're age 18 to 34, how did the probability change? Given that you're over 25, what's the probability you'll be in a car accident? Lower, okay, we'll charge you less. Anybody hit 25 yet? Anybody, 25 is way in the rearview mirror. So you guys, the day you wake up when you're 25, you suddenly know how to drive. So, right? So you guys, if you haven't hit 25 yet, it's a beautiful day because your insurance goes down. Unless you were just in an accident, like, what the hell's wrong with you? Don't do that shit around 25. Your insurance goes way down, and you're like, all right, I know how to drive. No, you don't. Do you guys kind of see what I mean? Probabilities are used in insurance types of things all the time. This is why they want to know, are you a good student? Because good students are less likely to do crazy shit. Believe it or not. Not always, but they're less likely. So, for example, people hear that incorrectly. So if I said I saw somebody in the distance getting off of a Harley Davidson, would you guess that it's a man or that it's a woman? You guess that it's a man. You just would, right? If you had to guess, you would say man. Why would you say it's a man? More men drive Harley Davidson. Does that mean that no women drive Harley Davidson? No. So when we say it's more likely or less likely, it's not to the extreme of nobody of these other people do this shit. No, that's not what that means. And sometimes in the news or whatever, people hear things wrong and they go insane and it's like, rein that shit back. Probability don't mean that. It just means what's the likelihood or not. It increases the likelihood or decreases the likelihood. Right? If you take this drug, it decreases the likelihood of this. Well, this happened to me, and then you have this big lawsuit. I'm like, no, they said it decreased the likelihood. You could still have it happen to you. Right? So all this kind of shit is so misunderstood. It drives us stats people a little insane, if you can tell. Okay, man, that was a long time to say that. Let's see what else I want to say. What about, let's see if I can push this a little bit. What if I said, what's the probability I pick a man or someone who said no? So there's 74 men, and 62 people said no. So 74 plus 62? Why is this not good? Who did I count twice? No. I didn't call all men twice. Here's the men. Here's the no's. How many people did I count twice? 51 people I counted twice. I counted them as being a man, and I counted them as saying no. And they're like, yeah, our vote counts twice. No, screw you. Men who said no. I got to subtract you out. Or you can be smart about it. When you give it a table, 74 men plus 11 men that I haven't counted yet. Because what's 62 minus 51? Of course it's freaking 11. It's the rest of the men, right? Okay, all right. Slow down. So again, today is just an overview of ideas. We're going to drill a lot deeper into these. We're going to develop formulas. We're going to look at different formats. This is one format to have probabilities given to you. All right, let me let that sink in for a bit. Out of what? What goes on the bottom? 132. Because did I give you any information about this person? No. What's the probability that it's a man or somebody who said no? I don't know who the hell the person is. It could be anybody. I didn't give you any information. So what do you get there? 85 out of 132, which is 64%. All right, just to finish that out. I like it. Cool. All right. So let's take a step back here. Let's see. I just wanted to throw that out there, see what you knew already. See what kind of reactions I would get. Has everybody got what they want from this? More than you wanted? I'm going to erase it. That's why I'm asking. So you guys will look like, yes, you're good. Okay. Oh, let me tell you this little story. A friend of mine, a while back, about 10 years ago, she wasn't married yet. She wanted to have a kid. And she was in her 30s. And she's like, Jeff, I heard that this condition for babies, the chances of that doubles after you get a certain age. And so I did some research and I said, okay, my friend's name is Eva. I'm probably going to say Eva. I said, okay, Eva, it was 0.03% chance of happening, and now it's a 0.06% chance of happening. So sure, it doubled, but that's still not like that crazy, right? Don't just run out and grab some dude and have a kid. Maybe you can rein that back a little bit and find the right guy, but she did, and now she's got a beautiful little kid. But you've got to be careful about stuff like that. You hear that kind of thing all the time, and they don't show you the numbers. They'll just say your chances double, and you're like, no, show me the freaking numbers so I can make a decision on what that is. If it was 25% and now it's 50, all right, well that's some concern. Right? It was 1 out of 4. Now it's 1 out of 2. Holy shit! I'm going to be concerned about that. But 0.03 to 0.06? No. Come on. Twice as many happen, sure, but twice as many as almost 0 is still freaking almost 0. Right? Okay. That little tiny thing I want to say. So let's talk about a little terminology, and then we'll head out a little bit early. All right, thought that might wake you back up. I'm so happy that the best part of my class is when I tell you we're going to leave early. Some terminology. All right, this word we should all know. We have an experiment.
Is this chapter 3?
This is section 3.1.
What about the last thing?
Say again?
The chart, was that 3-1 as well?
Well, the chart was sort of all over chapter 3, to be honest. But we didn't do any formulas yet. I was just throwing some ideas out there, just to get you in the mood of probability. So an experiment could consist of trials. So trials might mean I flip a coin 10 times, so there are 10 trials of flipping a coin. I like that, right? So for any experiment that you conduct, if there's some trials or whatever it is, there are various outcomes. So let's say we're doing this, let's say we're having 3 kids. A couple plan on having 3 kids. Cool, I like it. So there are various outcomes that could happen. Give me some ideas of outcomes. I like it. Well, let's outcomes based on gender.
Old girls, old boys.
All right. So here's let's be very. Let's say it could all be girls, right?
2 girls and 4.
How many things are we gonna write here? How many? Yeah, exactly. How many choices are there for the first kid? 2. And I'm not going to get into any gender issues. This is purely the gender that you're born with, and it's a very small percentage that are born with both genders or not quite a gender. There's a very small percentage. We're going to just say boys and girls. I'm not going to get into any controversial, nifty shit. I'm going to leave that up to South Park and ineffectual CNN commentators. So you got they could all be girls. Or it could be girl, boy, girl, boy, girl, boy, boy. Now, I'm doing it in a very specific kind of order so I don't leave anybody out. I kind of float a dude through, float the dude there, float him there, and then I have 2 brothers. with an older sister. That was 3 brothers and an older sister in my house, and she kept, oh, Mary, you didn't want to cross her. Now, what if the boy was first? So it could be boy, girl, girl. And see how all these are going to repeat? It's a nice way to keep this. So it could be boy, girl, girl, boy, girl, boy, 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 girl, boy, boy, boy. All right. So each of these is an outcome. If I collect all the possible outcomes, that is what is known as the sample space. Why would we call this a sample space? Because from that space, I can sample possible outcome. Holy shit. Sorry, I mean, yes, that's why. So for example, now what am I going to assume here that's not quite perfectly true, but it's close enough? What do you think I'm going to assume here? Or maybe some of you guys didn't realize it's not quite that. I'm going to assume that the probability of a girl and the probability of a boy are the same, and they actually aren't. Nature somehow knows, bless you, if you saw the original Jurassic Park, you know that nature finds a way. And it knows that men, we die earlier on average. It's just the truth. It's just the way it is for us. So the probability of a boy being born is a little bit higher than a girl because we lose us boys at a higher rate than girls. So somehow, I don't know how, nature just kind of knows. But let's assume it's like 50.2 and 49.8 or something crazy. Let's just say they're both 50-50. Is that cool? They're both 50%. All right. No sticklers out there. Good. Thank God. So I'm saying that the probability of a girl and the probability of a boy equally likely. And this is kind of new to us. Doesn't this look a lot like, what was this notation in algebra? Function notation, right? So it's an f of x, f of 7, for example. Probability of girl, probability of boy. Oh my God. So that's a quick way of saying probability of something. I like it. Cool. So what is the probability that I get exactly one boy? Well, how many total outcomes are there? 8, right? 2 times 2 times 2 is 8. That's why there's 8 outcomes. I like that. All right, 2 options times 2 options times 2 options. That's why there's 8 options up there. Out of those 8, how many have exactly one boy? 1, 2, 3, 3. You guys see that? So there's a 3 out of 8 chance that I'll have exactly one boy. I like it. What's making this easy is that these are all equally likely. If the probability of girl was 60% and the probability of boy was 40%, what would be the most likely thing up here? If girls were 60% and boys were 40%, the most likely thing up here would be all girls, of course. But they're equally likely, so I can say they're all the same likelihood. So I can just say there's 3 that match what I'm looking for out of 8. I could not do this if they were not equally likely. We'll have to learn that math a little bit later. So this, you can see this is sort of the same thing we were just doing earlier. What's the probability that I get more than one girl? So more than one girl means 2 or 3. I like it. So I got 1, 2, 3, 4. That's it. 4 out of 8. 1/2. 50% chance. I like it. I like it. You guys get that so far? Is that cool? So I'm trying to show you a specific example we can do some math on while we're also talking about these crazy ass definitions that are often very boring. Blah, blah, blah. I want to make sure I don't leave anything out. The book's got blah, equally likely, beautiful book. All right. Now, there's something called, all right, let me ask you this. This is applicable today, because we actually had frickin' rain today. which I never thought I would miss, and I miss it now. We had freaking lightning
Thunder.
and thunder and all the car alarms. I hate that. Boom. Help me. But if the probability is going to rain today was 40%, what's the probability it was not going to rain? 60%. That's insane. Why? That's easy because together they have to make 90%. We call these complementary events. It's kind of nice. They complement each other. Oh, they don't tell each other, oh, you look good, you look good. They fill each other in a way, right? They make 100% together. I don't know if you guys remember from geometry, complementary angles made a 90-degree angle. Some of you guys are like, stop now, Jeff. That's in my past. Complementary. I gotta use the same symbol as the book. I always forget which. I think they use a stupid little prime. They do. All right. So the probability. So A prime is the complement of A. So what's the probability of A prime plus the probability of A? 100%. They got to fill each other in. I like this. This might slip out sometime. I am used to writing A complement as that, which I understand is a little weird since we normally think of that as the average of something. But if that slips out, just say something, or don't. Just know what that means. I'll try to remember this book uses the prime as a complement, as the opposite in a way. I like it. All right, that's pretty simple so far. Blah, blah, blah. Oh, yeah. Blah, blah, blah. Blah, blah, blah. Oh, okay. So I think the last thing I'll do, and we'll get out stupid early. So you guys have plenty of time to go to the tutoring center and get help on your corrections. By the way, has anybody looked at their homework sheet and seen, well, that's an admission, and seen something other than the test down there? Ooh, look at you. Get that out. Yes. I mean, if I were you, I'd be like, what the hell's that, Jeff? What's that mean? Double quiz. You have to take it twice? So this is the only quiz I got listed on here because Chapter 3 is a weird chapter. It sort of lives in the middle of our statistics. I tried to do it first one semester. It didn't go so well, so I just stopped trying. So Chapter 3 gets its own little mini quiz. Double quiz, I'm sorry. Mini test I used to call it, and that freaked people out, so now I call it double quiz. All it means is it's about twice as long as the normal quiz, and it counts about twice as much. Hence the name double quiz. So we're going to have some practice handouts to do in class. I'm going to actually have a practice probability quiz, like a practice test with an answer key. You guys understand? It's sort of a standalone chapter. It'll show up again on the final, but it won't be on the next test. Not directly. All right, is everybody with me? That's to explain that double quiz that apparently nobody realized, but just in case somebody did, I want to let you know what that was. Conditional probabilities. We did this earlier already. This is the one that was probability of A given B. Does this book use... Oh, thank you, book. All right. A better way to write this is A given B. I think it's a better way. Unfortunately, everybody thinks that's a division bar. It's not a division bar. It's straight up and down, and it just means given. It's just a shorthand way to say given. So can anybody tell me, with that statement there, did event A or event B occur? Which event do I know happened? B, because it says A, the probability of A, I don't freaking know, given that B happened. All right, cool. So let me give you a couple of different ways to think about this. How many guys, anybody not know anything about cards? Like, do you guys know the suits in cards? What are those? Hearts, diamonds, spades, and Clubs, I like it. Clovers, if you like Lucky Charms. Green clovers. Whatever gets you through. I like it. It's like, I'm just not violent. I like the idea of clubs. Clovers. Alright, cool. What kind of cards are there? Anywhere from, you can call what low? You can call the 2 low. And the ace is high, sure, right? That's the way I will normally do it, probably. And then you got, what cards have faces on them? Jacks and queens and kings. Everybody understand that much? We're not going to suddenly do Texas Hold'em and it's going to be your grade on the line. No. Right? So you guys are like, yeah, I can do that shit. Alright. You would think that I'd be really good at cards, but I have no poker face, man. I just can't stop. I'm like, oh! I need giant glasses, you know, to cover my whole face there. That would probably not go over big. So, let me ask you this. What if I pick so there's 4 suits, just in case somebody's not speaking up about knowing. There's hearts, diamonds, spades, clubs. These 2 suits are what? Red. These 2 are black. How many total cards are there? So how many cards are in each of these? 13. Okay. No jokers. The jokers have gone out. And we're making some stupid little stop motion Suicide Squad remake. Actually good. Yes. Oh, thank you. It was okay, but it was not what it should have been. Yep. Yeah.